Good morning.
Good morning.
How's it going? Yes.
I didn't find for the homework 7, I didn't find this depleted stockpiles number in his book. Is it in there or do we have to look that up?
I don't remember. Did it say it was in the book? There's a couple things that said are in the book.
It said just look in the book for all the numbers in the table and find that number.
Okay. I will have to look at that because I can't remember. It's been a while, but thanks for bringing that up. And if you don't get an answer from me by the end of the day, email me and nag me, because I might forget. Okay, so we ended our last talk about boats, and we found that shipping by rail and by boat were the most energy efficient, but that boats were really slow. And we found that you can't get boats to speed up because once they get to the point where they're making one bow wave, they're always going uphill, and after that the amount of energy it takes to increase the speed increases exponentially. Trains are very low energy, they're very efficient, but of course they can only go where the tracks are. So that's where we left off. Oh, and then we talked about air cushion vehicles, and we watched this very fun video about this crazy Russian plane. And then I realized afterward I had a couple more slides on this after that. So this was the Ekranoplans that we looked at that went over the water, and it had an air cushion, it had no rolling resistance, doesn't need to throw air down to get lift, but it still has wind resistance. So McKay estimated about 2 kilowatt hours per ton kilometer for that, which is about half that of a cargo plane. So it's more efficient than a cargo plane because it doesn't have to do the lift thing, but it can only go on certain surfaces. Here's another one called the EcoBoat that he talks about in the book. This was designed to run on biofuel, and there was actually a little sensationalism. He said runs on human fat. The guy actually did some liposuction on himself or had it done and saved that fat and made a little bit of fuel and put it in that thing along with a lot of other fuel. This thing is a wave-piercing trimaran, so it's got 3 hulls that pierce the waves. And McKay says, so it can go through waves instead of over them, but McKay says it actually uses more energy than the Queen Elizabeth II, and anyways it sank. So we don't have to worry about it anymore, but just for completeness I wanted to throw that in. So summary, boat transport is the most efficient, but it's limited in speed. So that's why we use boats to ship things across the ocean. All right, so let's talk about biomass. And we talked a little bit about this earlier in the course. And now we're coming back around to it because maybe we can have biofuels. Maybe that would be a way to improve efficiency of transport. So it's the ultimate solar energy because bio stuff comes from the sun. You can think of a coal substitution if you burn wood, for example, or something, some kind of solid fuel, or petroleum substitution if you're generating a liquid fuel such as ethanol. You can also think about it as food for people or animals. And you can also burn agricultural byproducts and generate heat to drive something. So the question is net energy produced? So you have sunlight here, 100 watts per square meter. Carbohydrate energy delivered by plants is 0.5 watts per square meter. So there's a huge loss right here, which we knew from earlier before. This is shown as positive, it's green. Then here we have additional inputs required for farming and processing, so that takes away from your net goal. And then the question is, how much delivered energy do you get? So this bar here is energy used or lost in farming and processing, so it could be depending on the crop. And what you get out of that is some net amount of energy. So we'll take a look at this, but we're going to ignore embodied energy costs in what follows here. So coal substitute. So you could grow willow or miscanthus or poplar and burn them. So they consume an average power of about 0.5 watts per square meter of land. If you compare that to incident solar energy of about 100 watts per square meter in the UK, then the efficiency sun to plant energy is less than 1%. Well, you take those things, you grow them because the sunlight's free, you burn them in a power station, you have 40% efficiency plant to electricity. Okay? So the resulting power is 0.2 watts per square meter. And then looking at Ohio, if we said we cover 1/8 of Ohio, because we had solar panels and windmills on parts of the other, in our houses, parts of Ohio, end up with 6 kilowatt hours per day per person in Ohio. and compared to Britain, he figured he could get 2.5 kilowatt hours per day per person. Again, we have better sun, we have more land per person. So that's a possibility. Since it's Ohio, we'll grow switchgrass. Okay, that produces ethanol. You can get a net energy of 6 megajoules per square meter in a year. If you include the fertilizer, diesel fuel, etc., comes out to about 0.2 watts per square meter. So we're back down to the number we had before. The greenhouse gas emissions for cellulosic ethanol derived from switchgrass was 94% lower than estimated greenhouse gases from gasoline in this particular study that I've cited here. So even if you don't get a ton of energy, there appears to be some benefit in greenhouse gases, at least according to this study. Petroleum substitutes in the UK, rapeseed, they can make biodiesel out of it, 0.13 watts per square meter. Sugar beets, we can grow those in North Dakota, 0.4 watts per square meter. That gives you ethanol, but that doesn't account for the energy input, so probably by the time you do, you're closer to the 0.2 number we had before. Now, Brazil has been growing sugarcane for some time now. They have the right climate for it. They can get 1.2 watts per square meter, make ethanol out of it, and they can also grow multiple crops for years. So in Brazil, they use a lot of gasohol. You go to any gas station in Brazil, every gas station has an ethanol pump and a gas pump, and even the gas has ethanol in it. And they were completely independent of oil, I believe, for a while. So Brazil is the second largest producer in the world of ethanol fuel. So the U.S., we make it from corn, they make it from sugar cane. All cars in Brazil use gasohol or ethanol, and they have a lot of flex fuel vehicles, including, by the way, a very large number of flex fuel motorcycles. People are talking about increasing the ethanol content in our gasoline in this country, and all the motorcyclists are getting upset because their bikes won't run it. They're more particular than cars, evidently. But in Brazil, there's lots of motorcycles. People are poor, so your first car is always a motorcycle, and then you move up to a car if you start to make money. So they have a lot of flex fuel ones. So the way Brazil did this was they did a lot of agricultural research. For one thing, they can grow 3 times more sugarcane per acre than they could even 30 years ago. So they made huge improvements in the varieties of sugarcane. They get more sugar. They bred sugarcane to be more resistant to disease. They can grow at more varied climates. They also improved the nitrogen fixation that the sugarcane was doing, so that improved the fertilizer situation because they didn't need as much nitrogen fertilizer. More sugarcane to ethanol. Then they had a problem. So if you look at this plot here, here's 2000 to 2001. They started with 10. This is production, 1,000 cubic meters. So this is 10 million cubic meters. No, 10,000 cubic meters, sorry. Ethanol production. And then it went up and it went up, and then it started to go down. So part of it was that people were saying the sugarcane was driving up food prices. That should say food prices. They had a couple of bad harvests around that time when it started to take a dip. And also what really was key there was that the government froze the oil price to control inflation in 2012. And so now as a result, so here this is showing ethanol for pure biofuels and ethanol for blending with petrol. This is a British report, evidently. And you can see this is 2008, 2009, 2010, 2011, started to drop off. Meanwhile, the number of vehicles in Brazil, the red is cars, the orange is motorcycles, yellow is vans, green is trucks, and blue is bus. And you see the number of vehicles is increasing, and their actual use of production of ethanol is decreasing. So in some places, it's actually cheaper to use gasoline again than it was to use ethanol. Well, when I was there in 2008, it was all, you saw ethanol everywhere. So if in the U.S. we don't grow so much sugarcane, but we can grow corn. So according to McKay, 1 acre of corn yields 122 bushels of corn kernels per year. That's 3.7 tons. You can make 2.6 gallons of ethanol per bushel. So that works out to our very familiar 0.2 watts per square meter. Energy inputs turns out to be 0.2 watts per square meter, so it's a wash. But you can also harvest the stover. So the stover is this stuff that's left in the field after you've harvested the corn. It's more complex carbohydrates, they're harder to break down. For every ton of corn, you get a ton of stover, so there's significant mass there, and maybe you can get 30% of that. So if you get about 3.7 tons per acre of stover produced, while 1.2 tons harvested, you can get 90 gallons of ethanol. Energy in ethanol is 6 kilowatt hours per liter. It's not as high as gasoline. So when I worked that out, I got 0.05 watts per square meter from just the stover. So earlier in the course, I said that it was pretty much a wash producing corn, ethanol from corn, but if you also include the stover, you get just a tiny bit of boost. Nothing like what Brazil gets out of sugarcane. Corn kernels to ethanol, no net gain. Stover to ethanol, we already counted for the energy inputs in growing the corn, so that 0.05 is now a bonus. But switchgrass is 4 times better. Here is a neat chart that compares Brazil's sugarcane to United States corn. So Brazil, sugarcane, United States corn, total ethanol fuel production in 2011. Brazil, this is megagallons, 5,000 and a half. United States, 13.9 thousand ethanol fuel. Total arable land, this is in mega hectares. Brazil is big, 355. United States, 270, not including Alaska because you're unlikely to grow crops for fuel in Alaska. Area used for the ethanol crops, this is what they're actually using. 3.6 mega hectares, that's 1% of their land. We're using 10, which is 3.7% of our land, of our arable land. Productivity per hectare, liters per hectare, 6,800 to 8,000 for Brazil, 3,800 to 4,000 for the United States. Partly because, again, sugarcane, they grow it 3 crops a year. Estimated greenhouse gas emissions reduction, 86 to 90%, 10 to 30%. We're having to use a lot of tractors and stuff. I suspect that's part of that figure, although I don't actually know. Estimated payback time for greenhouse gas emissions, Brazil 17 years. United States 93 years. I'm thinking we shall move to Brazil. Total flex fuel vehicles produced. 16.3 million in Brazil, 10 million in the United States. We don't have that many. Ethanol fueling stations in the country, 35,000. This is 100% of them. Every gas station in Brazil, because for a while they were mandating that you had to have, well, I don't know about mandating, but there was ethanol everywhere. Every gas station has an ethanol pump, whereas only 1% of our gas stations do. The cost of production in dollars per gallon, 0.83 and 1.14. All right, so here's another kind of biomass, algae. It's the same efficiency converting sunlight to energy because they both use photosynthesis as terrestrial plants. But you can grow the algae in carbon dioxide rich water. And the carbon dioxide could be carbon dioxide collected from a power plant, so you can get rid of some of it. Could produce 0.01 liters of biodiesel per day. That works out to about 4 watts per square meter, which isn't bad, plus it uses CO2. We have some people at Ohio State doing research on this, and I tried to get someone to come and speak to our class, but they said no. So I don't have more to add, unfortunately. Then there's anaerobic digestion. So that's where you get bacteria to eat biodegradable waste like sewage sludge, delicious, or even crops grown specifically to have bacteria eat them. Anaerobic, by the way, means without oxygen. So there's a bunch of different kinds of bacteria. The first kind of bacteria break down insoluble organic polymers and carbohydrates. And then you have acidogenic bacteria that break down the sugars. You have acetogenic, that means vinegar. Bacteria convert results to ammonia, hydrogen, and carbon dioxide. Then you have methanogenic bacteria, converts that to methane and CO2. Nutrient-rich digestate, then can be used for fertilizer, and you burn them with methane. Okay, continued. So if you put that same stuff you're going to have the bacteria eat in a landfill, you'll still produce methane, but the methane goes into the atmosphere unless, of course, you figure out a way to collect it at the landfill and burn it for energy. The heat from the digestion can be used to control the temperature of the digester. It has to have some warmth in there. You can treat the methane that you collect and inject it into a natural gas grid, hypothetically. More likely scenario would be to use anaerobic digestion for energy and heat locally. You aren't likely to put it on the grid so much as use it near your home or in your neighborhood. All right, so we've been looking at transport. We figured out how to engineer better cars. We figured out how to engineer better airplanes. We concluded we can't get much better. We looked at the limits to engineering better engines, and we even looked at biomass as a potential gasoline substitute because gasoline is used for transport. So I think we've done all we can with transportation. So what's the next biggest energy consumption? What should we target next?
Is it heating and cooling?
It was heating and cooling. Bing! So that's what we'll see if we can engineer better heating and cooling. All right. So how much energy can we save if we improve our heating technology or, God forbid, change our lifestyle? To start this, the power used to heat a building is found from power used. Average temperature difference times the leakiness of the building, that would be thermal leakiness, divided by the efficiency of the heating system. Okay. The average temperature difference, that was the first term there, depends on what's the weather doing outside and where you set your thermostat. So thermos is Greek or Latin or something for heat, and statos means keep it the same. The thermostat was invented in 1883, and although modern ones are electronic, this technology is still perfectly good and you'll still find it in places. It consists of a sensor and some kind of controls. The sensors might be bimetallic sensors for that kind of thermostat, or a thermistor, which is just a resistor that's sensitive to heat. It changes its resistance with heat. Could be a thermocouple, could be some kind of semiconductor sensor, something like that. Okay, here's a household thermostat. So, this is the control pin where you set the thermostat. This coil here is a bimetallic strip. So if you unwound that coil, it'd be a long strip with two different kinds of metal, and they have different thermal expansion coefficients. So when the temperature changes, one expands faster than the other, or contracts, and so that makes it bend. So it curls up into this coil, and when the temperature changes, this whole thing kind of, when it gets colder, this thing kind of cranks this way. When it cranks this way, the moving end moves clockwise, wire connected to the heater control valve. So as this thing moves, this wire here is connected to the control valve. There's a moving contact connected to the bimetal. I think that's this thing here. And this moves back and forth. And then when it gets to a certain temperature, it gets close enough, it hits this, closes the circuit. It tells the furnace to come on or the air conditioning to come on. There is a magnet here. The idea is that if the temperature is really close to, if you're really close to where the set point is, you don't want the kind of tapping it and cycling on and off a whole bunch. So there's a magnet, so once it gets close, it snaps over, and then the temperature has to change a couple of degrees before, excuse me, before it separates again. It builds in hysteresis for you engineers. Anyway, that's kind of cool. 6 is a fixed screw, contact screw, that's adjusted by the manufacturer. You leave it alone, unless you're an engineer and you like to take things apart. Modern thermostats use a thermistor and electronics to control the heat. They're typically programmable. So that's the thermostat. Now let's talk about the leakiness of the building. So you've seen these thermal images, and where it is purple, the most heat is leaving the building. So how does heat leave a building? It leaves just by conducting through the walls. So conduction, well, you know what conduction is. One side gets hot, eventually the other side will get hot. And then ventilation. If you have cracks, gaps, ducts, any kind of holes, screen doors open, something like that. Both of these heat losses are proportional to the temperature difference between inside and outside. So the bigger the temperature difference, the more loss you're going to have. So conduction, the power loss is the area, so the area of that house, times U, where U is the thermal transmittance, and it will depend on the material, times the temperature difference. Area, basically how insulating is it, and temperature difference. Thermal transmittance U is measured in watts per square meter per Kelvin. Kelvin is temperature. It used to be degrees Kelvin when I was young. Have they taught you guys to just say kelvins, or are you allowed to say degrees? You don't say
Kelvin,
degrees
just Kelvin.
anymore?
Just Kelvin.
Just kelvins. How weird. What bothers me is that when you get to absolute zero, it looks like okay instead of 0 Kelvin. Right. All right, so a bigger U is bad. That means more power loss. Now, suppose you have two objects in series, such as a wall and an insulating layer, something like that. You got a warm room, you got a cold outside. The total thermal transmittance of this combination is 1 over the transmittance of one plus 1 over the transmittance of the other. For you electrical engineers, you immediately recognize this capacitors, but we'll think of it as heat this time. And here are some U values for some materials. So here's walls, solid masonry wall, 2.4, this is old buildings. Modern standards, so these are different materials. Outer wall, 9-inch solid brick, 2.2, 11-inch brick block, cavity wall, unfilled. So you know those, what do you call those concrete blocks? You know, they've got holes in them? We used to use them. Huh? Cinder block. That's a technical term. So if the holes are filled with air, 1. If the holes are filled with some kind of insulation, 0.6. Modern standard, much better, 0.4 to 0.45 to 0.6. Best methods, you can get U down to 0.12. Floors, suspended timber floors, 0.7. Solid concrete floors, 0.8. And I'm thinking suspended means it's over space, whereas this concrete floor would be a concrete slab in direct contact with the ground. But they think they can do better. Modern standard, 0.45. Best methods, 0.14. Roofs, again, here's a flat roof with 25 millimeters of insulation. That's not much. Pitched roof with 100 millimeters of insulation, that's a little bit better. He claims he could get down to 0.12. And then windows of course are a big source. So single glaze, 5. Double glaze, 2 layers of glass, 2.9. Double glaze with a 20 millimeter gap. Triple glazed, down to 0.7. So this is interesting. Triple glazed is better than current best methods. I don't understand that.
Yeah.
And these things that are outlined, I don't know if you can see, this is outlined, this is outlined. You can't see them on here too well, because these are things that he had in his house when he went and fixed it up. So, a brick wall that has U1 of 2.4 is lined with an insulating layer with U2 of 0.6. So what dominates the total thermal transmittance factor? So you have a wall with an insulating layer. Is the transmittance controlled mostly by the insulation or the wall? Or if the wall is really thick, it doesn't matter? Or maybe they're both equally important. So to do this, we use our engineering think, and we go, well, U1 is big, that's the wall, okay, and U2 is small, and since they're in the denominators, if this is big, this is small, and this is big, so what dominates the overall equation?
They're equal.
You think they're equal?
If one's small and one's big.
Yeah.
Depends.
So if this is big, then this is going to be bigger than this, so this is going to be less significant, right? Whose eyes am I looking at? I don't know. Whoever said that. I think it's you. Yeah. So I think that this is going to be the most important, and that is the insulation. So even if you have crappy walls, putting insulation in will make a big difference. And the better the insulation, the better the difference. So the take-home lesson is no matter how bad your house is, insulate it. The insulation matters more than the walls. Here's a picture of a guy I just love watching. Have you seen these videos like on Home Time or something where these guys, they spray this stuff and it's just this thin goo and then they just stand there and goes, it puffs up. Have you seen this? It's very fun to watch. You have to watch like This Old House or something. They spray it in. But the thing is, to do this, the walls have to not already be there. The outside wall is there, but you can't do this after the fact. Well, you can, but it's not easy. All right, so that was the thermal transmittance. So how good are the walls? Now, what about ventilation. So if you have cracks in your walls, and also we need air to breathe, so it's good if there's some ventilation. If you think the volume of the space is V, and the heat capacity, C, which for air is 1.2 kilojoules per cubic meter per Kelvin, and you have a temperature difference, delta T, between inside and outside, then the power in watts is C. This is newtons per hour. I think maybe I converted that. It can't be newtons. What is this N? Oh, N is the number of changes of volume of air. So how many times you exchanging the air in the room per hour, times C, times the volume, times the temperature difference, and I plug in these numbers, I get 1.2 kilojoules, blah, 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 N over, there's a number of air changes over, this is an hour in seconds, here is the volume in cubic meters, because I'm putting everything into MKS units, and it just so happens it works out to about a third, NV delta T. So what should we reduce? If you want to make the left side small, what should we make small on the right-hand side? It's a trick question. Everything. Duh. Everything. So we want to reduce the number of air exchanges, so how much air passes in and out of the room. We need to reduce the volume of the house, so that's a tip to make your house smaller and avoid cathedral ceilings, which is just a whole bunch of volume that you have to heat. And reduce the temperature difference between inside and outside. Because he lives in England, he's thinking mostly about heating. But of course, here we also have to think about cooling because we do an awful lot of that. So in the summer, it would mean turn up the thermostat. And one of the things that we need to do is figure out how much of an effect can that have. So if a kitchen has N is equal to 2 exchanges of air per hour, meaning all the air in the kitchen is replaced at least twice per hour, because you like to breathe and get those cooking smells out. And let's say your kitchen is 3 by 4 in floor space with a 3 meter tall ceiling, must be nice. What is the power loss if the kitchen temperature is 20 degrees Celsius and it's freezing outside? So freezing outside is 0 degrees. So let's see, we have 1/3 of 2. The volume is 3 times 4 is 12, times 3 is, doesn't matter because I'm going to cancel it with this 3. So I got 2 times 12 is 24, and this is 20 degrees difference. So I think the answer is 480. Do you agree? Watts. So we review now that the conduction, the energy loss was area times U times the temperature difference times the duration. Ventilation and energy loss was the number of air exchanges, the volume, blah, 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 times temperature difference times duration. So in both cases, the energy loss is something times temperature difference and the duration. The sum of all the somethings is the leakiness, or a loss coefficient. Here's the temperature demand in Cambridge. So this line is at 20 degrees C. And most of the time it's colder than that. Here's January, February, April, May, June. Oh, look, it got above 20 a couple of times. Oh my gosh, it was a real scorcher. It almost got up to 25. What is that? I don't know, 80 degrees, something like that. That's England for you. So that's why he's focused on heating. And he has this many 91 degree days. I think I have that defined on another slide. But I'll just point out that these are Celsius degree days, so when you're doing some homework that might come your way, be sure to convert to Fahrenheit, or at least be conscious of which one you're using. And his point is that if he lowered his thermostat from 20 to 17, just 3 degrees, he has reduced all of this heating here, and he's improved his efficiency. Here's data for, I can find data for University of Toledo, so that's what I put up. It's in Ohio. Here's University of Toledo cooling degree days. This is Fahrenheit cooling degree days. So a degree day is how many days the temperature is however many degrees above whatever your set point is. And in the US, the reference temperature is 65. So this is how many days in July. The different colors here are different years. 06, blah, 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 who cares? And then if you take the average, normal is like this. So 250 cooling degree days in July, fewer in August, I'm amazed. September, and of course none in winter, and then it starts to crank up again. Whereas in the winter, the heating degree days are how many degree days above 25, or does the temperature, sorry, go below 65 that you would have to heat. In Columbus, the average number of heating degree days annually is 5,700 and change, which is actually about the same as England. That surprised me, as Cambridge. So in terms of cold winters, ours are comparable to theirs, at least in Columbus. But the average cooling degree days is 797 for us, almost 800, and it's 163 for Cambridge. I converted their number to Fahrenheit. So their summers don't get as hot, but our winters are equally cold, which is why McKay's not so interested in air conditioning. Yes?
I'm confused on the definition of the heating degree and cooling degree days. I thought that you had just said that it was just how many days go over 65.
By how many degrees?
Oh, okay.
Yeah.
I missed that.
Yeah.
All right.
That's because I didn't say it very clearly.
Okay.
But apart from that, all right, so temperature demand. So here's degree days per year, and this is thermostat setting in degrees C. So let's say that you lived in a place that had 3,188 cool, heating degree days referenced to 20 degrees C. So this is where your thermostat is. And if you live in the same place and you turn your thermostat down to 17, you're down to 2265. Notice that this is a significant, this starts at 0, so this is a significant chunk. You wouldn't think 3 degrees would make that much difference, but look at that, it's a huge difference. Doesn't have the number on here, but I would guess it's at least a quarter, or around a quarter. And here's a cooling degree day. Again, you can improve just by changing your thermostat up 3 degrees. You can make a huge difference. This has got to be Cambridge data. So if the winter thermostat setting is reduced, oh man, it gave it away. The thermostat reduced from 20 to 17. Temperature demand for heating is reduced by 10%, factor 2, 30%, 80%. I think we concluded it was about 30%. That's a lot. 3 degrees. If the summer thermostat setting is raised from 20 to 23 degrees C, so now we're jacking up the temperature in the summertime, the demand for cooling is reduced by, and here's Cambridge data to look at. So if we raise the thermostat from here to here, for Cambridge, mind you, we would reduce the demand for cooling by 80%. Wouldn't be 80% in Columbus, but it would be something. And it may be a subject of a hypothetical homework. That's Cambridge. So energy loss and consumed energy. Energy loss is leakiness times the temperature demand. So what provides the energy, the heat in the house? Is when he says energy, he's thinking about heating because he lives in Cambridge. So there's some heat by the heating system. There's you having hot sweats or whatever, and you've got gadgets that give off heat. Maybe you've got the slow cooker making some chili to watch the game. When is the game?
Tonight.
Huh?
You're talking about
The final basketball game.
It's tonight.
Tonight?
Yeah.
Okay, so you gotta make chili. You maybe have sunshine in the windows. So the energy consumed is the energy delivered divided by the coefficient of performance. So how can we reduce the energy consumption of a building? We could reduce the temperature demand, which means adjusting the thermostat. And that means adjusting our lifestyle to some extent. I know there are plenty of people who don't want to wear a sweater all winter long. We could also reduce the leakiness. So we could have better buildings, civil engineering, better materials. Civil engineers, well, it doesn't matter. Better materials, insulating materials, better windows, for example, and that will increase the coefficient of performance. Well, this is engineering better heating. So I guess coefficient of performance would be better heaters. That's the energy delivered over the coefficient of performance tells the energy consumed. So we need better heaters. So these are 3 things that we can do, and we can attack all of them. We can change the temperature demands. You can turn down the thermostat and wear a sweater. For every degree Celsius, you use 10%. You have 10% less heat loss. So if you go from 20 degrees C to 15 degrees C, you can cut your heating bill in half. And he talks about a woolly jumper. I had to look it up. Evidently, that's British for sweater. Or we can deal with being hot in the summer. And I know a lot of people find that difficult. Here's a doggy with a block of ice. But you know, that's got to be stage picture, because if a dog is hot, what's it doing? It's panting. It doesn't have its mouth closed like that. All right, so the discussion is, can you learn to deal with the heat? I don't know. What do you guys think?
My house all winter hasn't gotten above like 59.
Really? Is that intentional, or is that because it's so
We
leaky?
got like a huge old house and it
Yeah.
costs $1 million, so it's
Oh.
intentional.
Yeah, our first heating bill was really bad, and so then we decided to, like, we were doing it like 60. Usually it's suggested to do like 68.
Yeah.
Like, that's suggested, but usually most houses do like 71.
Mm.
But then with our house, even doing 68, our gas bill was just awful. So they could put it down to like 63, 65, and just everyone just understood that they had to be wearing a sweatshirt. Like, they can't
Mhm.
complain if they're not wearing a sweatshirt.
And then it's
So-
okay to complain?
No, still, it's just we can't have it
Right.
much higher because it's just way too expensive. Our house just had awful drafts, and
Yeah.
the walls are plaster, so it's
Uh-huh.
like the heat goes right through the plaster walls.
Yes. You don't think there's insulation behind the plastic?
No, there's not.
There's not. You know that for a fact.
Yeah.
Is this a house you own, or are you renting?
That is renting.
Yeah.
It's been around for 100 years.
Yeah. So it's not in the landlord's best interest to insulate that, because he's not the one paying for the heat, and he would be paying for the insulation.
My apartment last year, I didn't have to turn the heat on all winter.
Neither did I.
I lived in like this little brick box.
Yeah.
Worst air circulation ever. It was just like gross. Like I would go home
Yeah.
as many times as possible because I felt like my apartment was making me sick.
Oh.
My apartment did not get below 68 degrees without turning the heat on a single time.
Did you have windows, or any exterior
2.
walls?
We had 2 windows.
So one exterior wall, or two?
Yeah. Yeah, we were like, we had one on each side and
Uh-huh.
above us, but we didn't have to turn it on once. It was pretty
Yeah.
awesome. My bills were like $2.
When I was in college, I had an apartment on the second floor of a house, and the landlady lived below us, and she would come up and turn up our thermostat because we paid for our heat, and that way she wouldn't have to have her heat, because she would get heat from us, I guess, or we would insulate her. We would provide a small temperature difference between her and the outside across the room.
Yeah.
So we do 3 heating bills. She was weird. She also accused us of cooking squirrels.
Were they
Well,
good?
she wasn't that far off the mark, because my roommate was a forced ecology major, and she had to take a course in taxidermy. She did bring home a squirrel carcass. She had to boil it down to get the bones and then build a skeleton. But she thought we were doing this all the time.
That's gross.
Yeah. Yeah, she made this cute little stuffed mouse, but before she put the eyes in, you could see the cotton through the eye hole. Well, okay, that's not part of this course. All right, well, so what about the summertime?
We'll see. My house doesn't have air conditioning for the summer on campus.
Does not have air
Does
conditioning?
not.
So you deal with the heat. You deal with the...
Yeah, we'll see. I might be going back to my parents' house for the summer just so I don't have to deal with that. Our dorms freshman year on South Campus didn't have air conditioning.
Right.
And that was like in May and June. That was pretty bad.
Yeah. And now the students are going to be coming and living there in August, which will be very bad. So, but aren't those geothermal wells on the south level going to help with that?
Yep.
If they ever work.
God, I've lost like 3 or 4 physics classes because they're putting those in Smith too. Or they're doing something with big tubes and hydro cooling or
Yeah.
something like that. And they had like the wrong drill schedule, and you just haven't been able to hear our lecturer the entire class period. We finally on Friday, 2 kids from our class went down and just like told them that they had to stop drilling, and they believed us and stopped drilling for the last like half hour of
Oh,
class.
really? Wow.
That was very annoying.
I don't remember if it was Scott Potter or someone else that I talked to. Scott Potter, when he was here, didn't he talk about that they drilled those things down, found out that the rock was all broken, and so everything was connected, and they had a sheath. So that must be what the concrete's for. So we're accustomed to having our air conditioning, and we'd get a lot of pushback trying to get people to live with
I
it.
love it.
hotter.
I'll be honest. I love air conditioning.
Yeah, I do too. I do too, especially when you're trying to sleep. Yeah.
I'm from the west though too, and so the humidity really makes a huge
Yeah.
It really bothers me even more, you know, because
Yeah.
I'm not used to that.
Yeah. It does. It plain makes it more uncomfortable.
Yeah.
So, and that's a huge part of air conditioning is dehumidifying the air in the summer.
Dr. Walter at Mechanical Engineering right now is developing a new air conditioning system, and it's like in this second or third stage of like prototyping or making a working model, and it like works like on spending, really focusing on the idea of dehumidifying.
Yeah.
So it's like a decanting wheel, and it's able to like, get away like, a lot of the moisture to like really help with that heating effect of humidity. So I guess he's working really hard on that with a lot of students.
With law students?
No, with a lot of
Oh,
students.
I was going to say law students. What do they know? Interesting. Yeah. So if you can reduce the humidity, you can be comfortable at a higher temperature. That's what you were just saying.
Yeah. Well, and we used to just use what we call a swamp cooler.
Yeah.
They don't have those out here.
We can't because we don't
No.
have enough humidity.
It wouldn't
And we have
work.
too much humidity.
Yeah, it doesn't work, but basically it's just a big, huge fan that you stick outside your house where water just drips down the sides and it just blows in the water and it really cools your house nice, but not here.
No.
Where's the water coming from?
You just like it's like a little hose you stick out on your you plug it in and it's just outside, yeah. It just drips down the sides and blows in nice cool air. And it's nice because, you know, because it's so dry out there, it's nice.
Yeah, you want the humidity.
You do
too.
want the humidity.
Yeah.
Yeah.
Not like here, it's just hot and sticky. All right, so leakiness. Here we have a detached house with no insulation, semi-detached house with no insulation, and a terraced house, whatever that means, with no insulation. 53 kilowatt hours per day, 37 and 30. Now he says, suppose you have a loft, that's British for attic, evidently, and insulate the attic. So you insulate the attic, 43, you get down 43, 29, and 23. Now let's say you have those cinder block walls and you insulate the holes. You go take it down to 30 or 20 or 18, and then you replace your windows with double glazing windows, and you can get down to 27, 19, and 17. And the other trick, of course, is to simply live in a smaller house. This is what I want to do. I want to move to a smaller house, and I want to have, if it were up to me, if I could have air conditioning in my bedroom, I wouldn't care if I had it in the rest of the house. But, of course, all houses have central air, and that's a nuisance. So the author was really obsessed about this. That's why he wrote this book. So he was keeping track of how much energy, what his heating bills were every day, and he calculated it in terms of kilowatt hours per day per person. And started off, you know, there's some weather variations here. This was a particularly cold year. And then he installed a condensing boiler. We call it a condensing furnace right here. And all of a sudden, his energy usage went down. And then at this point, what did he do? He put thermostats on all the bedroom radiators. He moved the hot water tank and new heating controllers, all programmable temperatures. I think that's what happened here. And look, I don't know if this is a full year yet, but it's the significant. The X's are much closer together. So he's definitely using a lot of energy. And he lives in a very old house. He went from 50 to 32, but his goal was to reduce his carbon footprint to less than 1 ton per year. And so even all of this stuff was not enough. So then he installed cavity wall insulation, attic insulation, replaced the doors so they're double glazed, so he must have windows in his doors, that's all I can think of. and he paid attention to the thermostat settings, and here's the difference here. More insulation, more glazing. And if you compare this to the years before it, yes.
What's the curve?
So he's plotting he's plotting his,
he's
his
plotting
energy
over a
bills.
year.
Yeah, this is years.
Oh, I see.
Sorry.
Okay.
Yeah, I didn't tell you that. This says gas use.
Yeah, I saw it was years. I didn't realize that the curve was for the full year.
Yeah. So he reduced his heating bill to 13 he started at 50-ish. Well, these years were 50. These years, who knows? Maybe he had kids and he had to turn the thermostat up. I have no idea. Okay, so here's his house. You can see it's old. What helped the most? He doesn't know for sure, but he thinks it's a combination of behavior changes and building changes. His house is built in 14 semi-detached, which I think means that there's another house attached to the other side. Yes?
Did he mention at all how much energy he used to do all of these things to reduce the energy usage of the house?
You mean the embodied energy and the insulation and all that stuff? No.
Well, I mean, not even going that far, but just like, well, I guess you would have to do embodied, but I just feel like he did a lot of stuff that required a lot of energy, which in the long run will make a difference. It'll definitely help his like heating bill, but for that
So what kind of energy
year,
inputs are you talking about? Just so I understand what you're saying.
well, I guess the embodied energy of all, like the insulation, the windows, all that. I feel like his energy usage for that year of him making the updates to his house, he didn't really tell us how much energy went into his house.
He did not include that. And you're right, you would have to include that. And furthermore, he put a huge amount of money into doing all this, you would think, and he's going to make that back. But his argument isn't to save money. His argument is to save energy, and he can demonstrate that right away. This says, look at some numbers. Here are some U values for some kinds of materials. No, sorry. Just different kinds of surfaces, I guess. So pitched roof, U value is 0.6, a flat roof is 3.
Why would that be the case?
I don't have any clue. Does anyone know why that would be the case? Why would a flat roof transfer more heat to the outside world? That makes no sense to me.
Yeah, it doesn't me
I'm
either.
pretty sure flat roofs are usually tarred. I mean, flat roofs are made out of a different material.
It could
So
be that could make sense.
Yeah,
Because it
I
just
believe
seems
the
like
material.
though if like snow was on there, it could help insulate as well.
True.
Longer, but
That's actually a very likely thing. And a pitched roof, remember, has more surface area, so there's actually more opportunity for conductive loss.
so it's got to be like what he's
It's
saying.
gotta be
There's got to
with
be
different
some
materials
material.
and
Yeah.
very possibly snow on the roof.
That and pitched roofs have, I mean, usually you're gonna have more air up there. Air is a decent insulator.
True.
That might make some sort of difference.
True. Well, so maybe that's, instead of a flat roof, there's actually that air cavity above the
Yeah.
ceiling. Maybe that's it. That would make sense. Vertical surfaces, extension wall, I have no idea what that is. Maybe it means non-load bearing. Main wall, thin wall. Single glazed doors and double glazed windows. Single glazed doors. What does that mean? I have no idea. Oh, maybe it's like a storm door or something.
Back to this roof situation.
Yeah.
What are his area measurements? Because if he's saying that,
Watts per square meter per.
yeah, but
No, the area, this column says square meters, right?
I didn't mean his units. I meant, is he saying that for 48 square meters, the U value is 0.6, and for 1 point, like I don't.
Yeah, well, these are measured per square meter. I think he's just giving a typical area because when you compute how much energy you're going to lose, you have to factor the area in.
Okay.
Yeah,
Yes. Oh, so yeah. So the third one, he's just multiplying them together
yeah.
for leakiness.
So total conductive leakiness, 232.4. I think this is, well, this must be his house. He must have places where there's a pitched roof and a flat roof because there's a small area here.
Okay.
So let's go back to a picture of his house. I have no clue. I was thinking that maybe he had something like this that had a flat roof, but that's still pitch, and there is a little bit of snow on there.
Maybe it's at the very top.
Oh yeah, I'll bet you're right. But that's above that's where the airspace is.
Yeah, I don't know.
And he's got a skylight. Oh, terrible idea. And he does have windows in his doors.
Did you say windows?
Yeah, doesn't that look like a window? Because he was talking about
window. I thought you said windmill. Like that makes absolutely
That's really efficient. Okay, so anyway, so here's his house, and then the ventilation. Here's air exchanges per day, and he has 3 in the hall. And the red numbers are things that he made changes in at some point. And he works out a leakiness number. And these units here, by the way, are in cubic meters. So he had a cubic meters, air exchanges, how many times you got to change out cubic meters. This is once every 2 hours. Things changed he made in 2006. He insulated his roof, he insulated his walls, and he double glazed his windows. And I don't remember what the thing about the hall is. That's in red. So he divided the leakiness by the footprint area to get the heat loss parameter. He came up with 3.7 watts per degree C per square meter. And if it's -1 outside and 19 inside, and you suppose you maintain that 10 degree difference for 6 hours a day, because I guess it's just the energy used during that 6 hours. You multiply these things out, it gets about 39 kilowatt hours. For 24 hours, if you figure out the temperature differences, you get 155 kilowatt hours per day. So it's easier than doing that is to use Cambridge heating degree days. So a heating degree day, reference to 19 degrees, 2,866 in Cambridge. So we have 322 watts per degree day is the rate of energy loss, 7.7 kilowatt hours per day per degree. Then you can multiply that out, convert the units, you get 61 kilowatt hours per day. If he lowers the thermostat to 17, the result is 48 kilowatt hours per day. If he raises the thermostat to 21, he would take more energy. So here's 17, here's 19, and here's 21. And this part here looks almost linear, but this scale doesn't go down to 0, right? Well, it can't go down to 0. I guess it could go down to 0, but it will. The curves we saw earlier were more curved. So there's 3 different things that can affect the energy required for heating homes. The temperature demand, we can't control the weather, but we can control, if we want to, what temperatures we can stand to live in. The leakiness of the house, so we can improve that with insulation, and how you produce the heat. And all of these can be improved. So the next lecture will talk about heating, the heaters, heat pumps and that kind of stuff. See what we can do. But there's room for improvement here, because I was worried after the airplane thing. How efficiently can be heat produced? Let me just see. Oh, that was the last slide. All right. Currently, fossil fuel burning is 78-90% efficient if you're just converting to heat. If you're making heat for the sake of the heat, not converting to electricity. So chemical to thermal energy. In a coal plant, it's chemical to thermal to mechanical to electrical. That's why those are 40%. So 78-90%. Next time, can we do better and get off fossil fuels? Can we have better heaters, more efficient? We'll look at combined heat and power and heat pumps. Okay, that is all I got for you today. I will remind you that I sent out an announcement about a seminar at CAR. Dad already forgot what it's about because it meets during this class time and I can't go. But you guys can go if you want to, because I'm going to record this lecture anyways. I sent you an email about it. I think it's Wednesday or next Monday. And it's about natural gas in vehicles, I believe. Okay, and I put up a homework and a quiz so you would be sure to have lots of fun. All right, run and play. I'll see you next time with a brand new show.